Venezuela holds the world's largest oil reserves, about 303 billion barrels. But here's the catch. Most of it is heavy crude, which can only be transported reliably through pipelines that run 24/7. And here is the danger. If the flow ever stops, the oil can literally freeze inside the pipes, causing massive, irreversible damage. To make matters worse, this situation became tougher than ever when the US government hit them with financial sanctions and banned trade with Petróleos de Venezuela, PDVSA. This basically froze many shipping routes, leading to a massive bottleneck across the entire network. That's why this 2,000-mile cross-country pipeline network has become a critical lifeline. Every pump station and every single mile of pipe directly impacts the national economy. In today's video, we're going to look at how Venezuela built this massive pipeline system to keep their oil moving. Stick around, because the engineering behind this is incredible. Don't forget to like and subscribe if you enjoy deep dives into large-scale engineering like this. To understand why this system is so critical, just look at this number. 60% of the Venezuelan government's budget comes from oil. This isn't just a resource, it's the oxygen for their entire economy. It all starts right here, the Orinoco Belt. Even though it holds over 200 billion barrels of oil, the geology here is incredibly tough. 90% of the output is extra heavy crude. It's as thick as molasses, making transport by truck or barge a hopeless task when you're dealing with nearly 9 million barrels a day. That's why they had to double down on a $7 billion gamble, a 2,139-mile pipeline network. The key here isn't just the large diameter of the pipes, but the tech behind it. They have to use heated pumping stations and constantly mix in chemical solvents to liquefy the flow, pushing it from deep in the jungle all the way to seaports like Puerto Jose for export to the US. That's the big picture. Now let's get down into the nuts and bolts of how these pipes are actually made. Even though these pipes don't have to cross harsh deserts like in Saudi Arabia, the unique nature of the oil means we need high-strength carbon steel. This material can handle two things at once: the massive pressure from the high-power pumps and the physical stress during installation. It all starts with massive steel plates, precision cut to reach an inner diameter of about 1.6 to 1.8 meters. The walls are thick, roughly 25 to 30 millimeters, built to withstand high pressure and decades underground. Then the assembly line feeds these plates into a multi-roll bending machine like this one, which gradually curves the steel into a perfect pipe shape. To seal it tight, they use submerged arc welding. This method creates an incredibly strong, deep bond that turns the bent steel into a solid, finished pipe section. Because welding generates intense heat, the pipes undergo stress relief treatment. This ensures the entire circumference cools down evenly. As the metal slowly shrinks, the weld stabilizes, making the pipe tougher and reducing the risk of cracks later on. After that, the welds are smoothed and the edges are beveled, getting them ready for the field. Each section is about 12 to 18 meters long to keep the number of field joints to a minimum. Before leaving the factory, every single pipe has to pass non-destructive testing. First up is ultrasonic testing to find any internal flaws. Then, X-ray scans check the weld quality. Finally, they check the dimensions and straightness to make sure there's no warping. Once they pass inspection, the pipes get a double layer of protection, an epoxy or liquid liner inside to prevent corrosion, and a polyethylene or epoxy wrap on the outside to guard against soil abrasion and moisture. Automated machines then move them to the yard, where they're stacked, marked, and sorted by batch. Getting them to the site is another logistical challenge. Most of these are shipped by rail because it's 60% cheaper than trucking. But when it's time to hit the construction site, specialized heavy-duty trailers take over for the final leg. So the skeleton is ready. Now comes the hard part, fitting this network into the wild terrain. These cross-country pipelines have to cut through mountains, swamps, and jungles. Engineers have to find the perfect balance between stable ground and easy access. To find the best route, crews use high-precision GPS and terrain mapping tools. Once the path is set, they mark it out with painted stakes. After the engineers give the green light, the land is cleared and leveled for the heavy machinery and construction teams. Excavators then dig trenches to the exact depth and width required. They sort the soil as they go. Suitable material is kept, and the rest is hauled away. In rocky areas, they use controlled blasting to break through the bedrock. This next part is crucial. At the bottom of the trench, they lay down a smooth bed of sand or sifted soil. This layer helps distribute weight evenly and prevents point stress on the pipe walls, which is vital because these pipes can shift over years of operation. Now it's time to put the skeleton into place. Workers line up the pipe sections in order. They also do a quick visual check on the straightness and the coating, just in case anything got dinged during transport. But we're not done yet. The pipeline has to pass a hydrostatic test. Engineers pump it full of clean water at a pressure much higher than the design limit. The goal is to sniff out any leaks or internal flaws. It's a mandatory step to ensure the pipe won't burst. Once everything is cleared, the actual assembly begins. Workers use 360-degree hydraulic clamps to perfectly align the centers of two sections. Then, a multi-layer automated welding system creates a rock-solid, consistent joint. Since this is a critical national asset, inspectors check every single weld using automated ultrasonic testing, AUT. Only after a weld is proven perfect do they apply a multi-component epoxy coating to create a seamless shield. Lowering the pipe requires serious gear. A fleet of side booms and cranes work together to guide the pipe into the trench. Because these pipes are so big and heavy, several cranes have to coordinate perfectly to keep the line suspended evenly as it's lowered into position. Engineers also survey the elevation and natural curve of the pipe once it's in the trench. They need to make sure everything connects smoothly, as any major misalignment could lead to leaks. Finally, it's time for backfilling and compaction. The first layer is that fine material to protect the pipe. The rest is packed down tight with heavy compactors. This ensures long-term stability and prevents the ground from sinking or shifting once the oil starts flowing. But construction is only half the battle. A system moving nearly 9 million barrels a day has to deal with thermal expansion, vibration from pump stations, and chemical corrosion. That's why the monitoring system is so vital. They use high-tech pressure sensors to track flow and temperature along the line to spot any leaks immediately. They also use a smart pig, a device that travels inside the pipe with the flow. It cleans the walls and scans for wear, cracks, or deformation from the inside out. And the real brain of the operation is the SCADA system. This stands for Supervisory Control and Data Acquisition. It gathers real-time data from sensors all along the route and sends it back to a central control room. SCADA lets operators keep an eye on everything: pressure, temperature, valve, and pump status, and gives an early warning for any abnormalities. This system is the gold standard for managing complex networks like Venezuela's. And that is the story of Venezuela's energy lifeline, a system that simply cannot afford to stop. If you enjoyed this deep dive into energy infrastructure, make sure to hit that like button and subscribe so you don't miss our next episodes. Thanks for watching.